Good evening, everyone, and welcome to All Space Considered, which I used to say at Griffith Observatory, except we're not at Griffith Observatory anymore.
Good evening, everyone,
and welcome. Someone has an echo on. So if everyone could mute themselves, except me, I don't believe I have that on. Welcome to the cosmic contemplation of all space. Are you all hearing that echo? Someone needs to mute. I think it could be one of our crew. Could everybody mute yourselves, please? Someone needs to mute. I think it could be one of our crew. Could everybody mute yourselves, please? So, my goodness, this is a rough start. So, Matthew, we're going to need some help here. And there, I think I'm not hearing the echo anymore. Ah, thank heaven. Nope. So, Angelica, you have the Zoom room control. Can you please just boot everybody out of it?
Everyone is muted. Do you want to check to see if a window opened on your computer?
Haven't changed a thing since rehearsal. My friends who are joining us tonight, this is Matthew, I'm going to ask you to take over control of the computer. I'm going to close down goal, although that's exactly as it was. Don't think that would change anything. I'm going to ask you to take over control of the computer. I'm going to close down goal, although that's exactly as it was. Don't think that would change anything. All right, I closed goal. I don't think that's going to change anything. Someone must be having, I don't even have the that cosmic start is over. I am going to start again, and hope that Matthew or David, you have control of the laptop.
Can you close all of Chrome and Safari? Can you close?
I am the guilty culprit, I believe. Yes, blame me. Yay! So this is a great way to start the show. I hope everyone loved that 33 minutes of like, what the heck is going on? I had it hidden, not closed. You're absolutely right, Matthew. So I was saying, I don't even have it open. And I didn't hear the sound, but it must have been filled somehow going back to my computer. So we're going to go ahead and just start over and pretend you just heard Bill playing that beautiful piece of piano music, which we will come to in a little bit. And so let me welcome you all to All Space Considered, not at Griffith Observatory, from our living rooms in our respective technology bubbles. And we are very happy to share with you a bunch of great stories tonight. So as you may be aware, All Space Considered happens on the first Friday of every month. Now that we are doing it from home, this is no exception. All Space Considered Remote is still from home. And so you can see our various social media tags on the right there. If you haven't already, please do follow us and find out more about all kinds of great events coming up, things to see in the sky, so forth. So with that, I am going to turn over to Bill the question. We heard all that music coming in, Bill. Do you want to tell us what that is all about?
Absolutely. Good evening, ladies and gentlemen, girls and boys and science lovers around the world. Here at All Space Considered, we love science, music, and fun. So tonight, as always, we'll be playing our music game during the course of this presentation. Our regulars already know the rules, but tonight they are, of course, adjusted to our current circumstances. You might have heard music playing on the stream prior to the show tonight. We used to call this our walk-in music when we were in a theater, but due to current circumstances, we now call this our log-in music. And each piece of music that you heard is somehow connected to at least one story we're presenting. If you can guess that connection, and you're the first one to do it during the course of the show, you win a prize. To make a guess, include the name of the piece of music you heard or some strong identifier and the story it's connected to. Enter your answer either here in the chat section or tweet it at us at All Space Considered. You saw the Twitter handle on the way in. Up to 2 prizes will be awarded for each song, one for the first correct chat and one for the first correct tweet. You can pick up your prize at the next All Space Considered we do once the observatory reopens. We have mission stickers, we have pins, pens, posters, prizes, alliterations, including calendars. That's another thing we have. This, by the way, is an example. I'll make sure you're seeing this. There we go. This is an example of a beautiful calendar that we produced. And this is a picture by David Pinsky. In this particular calendar, most of the images are done by David Pinsky. Now, who is a museum guide and a dear friend of all of us. Now, I want to say that the one little problem with this calendar is it's from 2019. So it's overdue. But as I've told you many times, you can reuse calendars, right? So a calendar from 2019 can be used again in 2030, less than a decade away. Just stick it in your sock drawer until December 31st, 2029. A 2018 calendar also would be good again in 2029, and a 2017 calendar would be good right around the corner in 2023. Reduce, reuse, recycle, and enjoy the show. Thank you.
Thank you, Bill. And I got to admit, what else is in your sock drawer? What kinds of things do you stick in your sock drawer for 25 years? I'm a little curious about that.
It's quite a collection. I need to organize that sock drawer.
Hey, now you've got all kinds of time. So all is well. I'm back and have the control of the laptop. Thank you, Matthew. And so let's get on with the show. Tonight is August 7th. And so the topics that we have prepared for you tonight starts with Mars is getting a rover. And if you've been at All Space Considered before, you know that we couldn't really go without at least doing this once.
Mars is getting a rover.
So Mars is getting a rover, but in fact, it's getting 2 rovers, and it's also getting 2 orbiters. So there's a lot of activity, a lot of launches to Mars, and David Reitzel will be telling us all about that. Then 2 more PJ parties from Patrick So. PJ stands for Parajove, and it's the Juno mission. And then we're going to tell you a little bit about how to make your own beautiful images from Juno. You've probably seen them on the internet and in social media, and you too can do that yourself. Then Jeff McKibben's going to tell us a little update on what killed the dinosaurs. We thought we'd set the stage early for the ways in which catastrophic endings can take place in nature, because we'll be coming back to that in the second half. Very exciting. I hope many of you watched the return of the SpaceX astronauts, the NASA astronauts on the SpaceX Crew Dragon capsule return safely to Earth. And finally, the August Sky Report. Then we'll take a short break, look at some pretty pictures of Comet Neowise, and refill your glass, whatever it is you might be sipping, take a short break, and then come back for the second half when we are very excited to have Dr. Katie Mack with us. Some of you may have seen Katie's presence on social media. She's got quite a big presence on social media, and she's written a book called The End of Everything, Astrophysically Speaking. So I guess this is the Armageddon cataclysmic show for early August. So with that, let's just get on to the next story. I hope that many of you have had the opportunity to go out every night this last several weeks and last couple of months. And in the sky, it's very hard to miss 2 very bright objects, Jupiter and Saturn. So I want to encourage you, if you have not seen them just side by side, traveling together through the night sky, that you do that when the show is over tonight or before you go to bed, and keep doing it all summer and early fall long, and watch how those two planets march across our sky. It's really quite a beautiful spot, quite a beautiful sight. And if you stay up a couple hours later, you will also see Mars joining the show. It's more of 1 o'clock in the morning, rises pretty late at night. So you have to stay up or get up super early to see it. But one of the fun things to think about when you're looking at Mars is that there are spacecraft there right now doing science. In fact, there are so many spacecraft. These are just the ones that are there right now, that are active now. We didn't even put in all the ones that have now finished their missions. So, Mars is a really busy place, crawling with human-made robots that are exploring the red planet. So, David, if you would, why don't you tell us a little bit more about some of the new spacecraft headed to Mars?
There we go, unmute myself, and I'm happy to tell you about it. This is the Mars Update 2020, the launch edition. If you've been paying attention to all the Mars launches, you've seen that we've been sending so many. The question is, why so many? What's going on? Why are we sending so many right now? Well, it all has to do with the fact that Mars and Earth were aligned on July 30-ish or so. They were about like this. It's close to the conjunction of Mars. Mars is close to us right now, and that's the time you want to launch. And what happens is about, 7 months later or so, on February 18th, 2021, that should say, my horrible typo there that I just catch now mid-show, of course. That's when we're going to arrive on Mars. And notice I have the green line smacking Mars down in there because we're going to land. We're sending a rover, which is super cool. So that's why you want to do that. It's actually a lower energy to get to Mars on this trajectory. If you launch when they're close, you don't have to use as much fuel. We could launch other times, but it would take longer and take more fuel. So about every 2 years, there is a launch window, and we just so happen to be at that launch window now. Of all things, 2020 brought us a Mars launch window, and we couldn't wait. Well, you could wait. The Europeans waited on theirs, and they're delaying that 2 years before they're going to launch their rover, so they weren't quite ready. The United Arab Emirates was ready, and they sent a mission called HOPE to Mars, and you're seeing the launch there. And the mission actually has, it's going to study the atmosphere of Mars and really look at the layering of it and see the composition and learn how it got to the way it is. It's only about 1% of Earth's atmosphere, so there's not a lot there. It has 3 main different cameras and an infrared spectrometer. It has a visible camera that's going to look at things, and also an ultraviolet instrument. So it's going to characterize Mars and Mars's atmosphere using those 3 wavelength ranges, which is pretty neat. In addition, the Chinese have launched. They're sending Tianwen-1 on a Long March 5. There it is being, well, that's not the actual mission being positioned, but that's the actual Long March 5 rocket. You can see this is the actual launch, however. It went spectacularly well. It was a beautiful launch. And they are sending, in addition to an orbiter, they're sending a lander and a little rover. And when I saw this rover, I thought, wow, they're building on the technology they used for the U2. U2-1 and U2-2 were moon rovers. And you can see they look somewhat similar with the mast and the top little camera and the solar panels that fold outwards. So I wish them luck. I think it's great that we're exploring Mars as a humanity going to Mars all at once here in this Mars launch time. So in addition, the Chinese are sending their rover. Let me see if I can point it out here. You can see their chosen site. It's not so far from the Perseverance site, actually. It's a large landing site. I'm sure they have it more narrow than that, but that's what I was able to discover. They are a little secretive about their mission. So there's the picture of a rover that was at some sort of tech show or something, a space tech show where they were showing off a model of it. Are you prepared for Perseverance to get there? That's, of course, the United States NASA JPL mission. You might say, well, that looks like Curiosity, and indeed you'd be right. It's built on a very similar chassis. There are some updates to it, updates to the wheels. They won't get as damaged, new instruments on board, but overall it's very similar. In fact, they're using the heat shield that Curiosity, the first heat shield they were going to use for Curiosity is the one that's going there, which made me wonder, was it discarded? But actually, I'm sure it will work great. If it worked for Curiosity, it's going to work for Perseverance. This is a picture I took way back when, it was like 2015 or something like that. Those are the parts for Perseverance on the floor of the lab where they built it. And here is a shot of it in that very same lab. no longer in crates, no longer in parts, and put together with the technicians trying it out. I like this little anime. Well, it's not an animation, it's an animated GIF of it in, I believe it was a vacuum chamber where they were testing it. And they were testing the equipment after they probably shook it, pumped out the air, got it down to Mars pressures. You want to know if it's all going to work. Here is the rover being stored in the nose cones. So those are the wheels folding up in there. You can see the sky crane above it. Maybe I should motion with the mouse here. You can see in the upper corner there, if you notice where my mouse is, those are the retro rockets of the sky crane that are going to help land it. Get a picture of the nose cone, moving along and getting to the exciting parts here. So here is the picture of the rover we want to send. And the answer is, the question is, did it go? And indeed, it did. Let's take a look at the beautiful launch video here. And the camera shakes a little bit. Imagine the rumble. And there it goes aboard Atlas V. So United Launch Alliance sends it off beautifully on its way to Mars. So our mission successfully launched to Mars, and separation went well. There was a minor computer glitch. It went into safe mode. Has to do with the fact there was a temperature sensor that was set a little too strict, it turns out. Somebody was a little thinking, oh, we can set this really strictly, and it hit that temperature limit, and it wasn't really out of bounds, but they did a reset, they fixed that, and everything seems to be safe. So a couple of beautiful still images of the launch. Well, where are we going? Perseverance is headed to a crater called Jezero Crater. And it's a very special place on Mars because there's evidence that water was there in large amounts. You can actually see what looks like an inlet channel in the upper right-hand corner. I'm moving the mouse along it now. And then you can see what looks like a delta. That circle is the landing area about where we want to come in. Actually, the landing ellipse is smaller than that, but that represents the landing area. And there's even an outlet channel coming out of this crater. So we believe this was once a lake that had deposits and sediment layered over a very long period of time down at the bottom. So an exciting place to go search for the evidence of microbial life. Whereas Curiosity was looking for the environments that life might be able to survive in, Perseverance is actually going to go look for the chemical changes, the chemical signatures that would be left behind with its instruments. And you can see here, there's evidence, these different colors or different minerals that are laid down in different aqueous environments. So there's actually evidence for different environments that might be better or worse at storing that signature, that fingerprint that we can go look for that says there was once life here. Now, in addition, Perseverance is heading down in there. It's headed pretty well. I just put it in context of the other landers here. You can see where inside is Curiosity. But the really special place about where it's going is that water that was there. We're going to land it with a sky crane again, bring it in that direction. After it lands, there is one very interesting little addition. It's this helicopter, Ingenuity, they called it, and they're going to test it. It's a test bed for some new technologies. Just like we first tested rovers with Sojourner, we are testing helicopter transport on Mars with Ingenuity. If it works well, maybe in the next Mars launch window, we'll be sending a bigger, stronger, more powerful helicopter to go explore more of Mars. Who knows? So stay tuned for that as well. Now, the instruments on board Perseverance were brought to us by an international range of folks. So this isn't just an American effort. I want to point that out, that we have help from across the world. And let me point out some of these instruments because they're really very great. Well, first of all, there's the super camera and the Mastcam Z. Mastcam Z is the zooming camera. You can actually zoom huge amounts, go from very, very close in to a huge wide panorama, a continuous zoom through that entire range with a couple of different cameras that are built on board. So no longer to get these panoramas do they have to stitch together individual little frames. No longer to get a zoom do you have to go in and zoom in with one instrument and pan it with the other. This camera will bring it all. In fact, we're going to be able to get 3D images because there's a couple of cameras that are separate from each other, just about the right distance of the human eyes, a little wider, it's about 9 inches, but still, they're going to be able to put together 3D images from about 6.5 feet up from the Mars surface. So look forward to being able to put on your VR goggles and really experience Mars like you were there. Well, like you were a 6.5 foot tall person. I'm never going to be that tall, so I look forward to that too. Now, Sherlock and Watson out here on the front with Pixel. This is sort of the business end where we're going to go looking for life. Pixel is an X-ray instrument. It's going to be looking at the chemical changes that could be left down by, say, a microbial mat. Now, this gets a little gross, everybody. You know the plaque that gets left on your teeth? Well, that's from little microbes. You want to get that scraped off. Well, on Mars, there were probably no dentists scraping it off the rocks. So it's left behind there. Perseverance is going to be able to see that microbial plaque of sorts. Whatever it was laid down with, the chemical change that was there, it has the instrument to do it. Sherlock and Watson use ultraviolet techniques to look for similar things. So Pixel's more about elements. Sherlock and Watson are more about organics and aerosols and things like that that the microbes would need to survive. The two of them together are really going to narrow in and say, this right here is a sign of life. There was life in this sample. It's amazing. Well, still, are we going to see the little microbes if there's little fossils there? No, that won't happen. Instead, for that, we're going to take actual samples and seal them up, and then we have to go get them. Now, whether it's going to be somebody stepping off of a rocket that maybe SpaceX is going to send, or someone else is going to send, or maybe NASA, or whether it's going to be a robot that goes and grabs it, we'll have those samples of these exciting regions to go look at it. So arriving February 18th, 2020, go looking for that. Now, we do have another rover that's already there. Curiosity is on Mars, and it's still exploring and giving us some beautiful vistas. You can see here this glorious image looking up Mount Sharp, this other amazing sort of cliffside here. And when you zoom in, there are these little nodules that are a clear sign that there was liquid water layering down this layer after layer after layer. So more signs that Gale Crater was full of water. This area kind of about halfway up the image that's lighter in color. It's a little difficult to see the mouse, but I'm circling it now. That's actually more clay. This is going to be the last chance Curiosity gets to go analyze clay deposits that we think are signs, again, that it was once habitable. So one more trek down, that is actually downhill a little bit, even though Curiosity's been heading uphill, to go look at these clay. In fact, it's reached there. There it is. And we're going to show you a picture of it drilling into that clay. So more clay samples are being analyzed from Curiosity. Now, what about our InSight lander? Are you interested in what's going on with that? I certainly am. It's an amazing little mission. It's gotten a little dustier over time, I do have to say. So we need to get one of those Martian dust devils to cross it and clean it off. But it's still working. It's still making Martian seismology measurements. It's measuring Mars quakes. That's a whole other story, and for another time. I'm interested in this mole. The little device on the left-hand part right next to that shovel is supposed to go down into the Martian soil and measure the temperature. Well, it's stuck, as you can see there. So they thought, well, we'll put the shovel next to it and it'll help it go in. That worked a little bit, but then that happened. It popped right back out, and we no longer, so what do? Well, they thought, well, instead of next to it, let's just push right on top of it. And indeed, that did work. It managed to burrow itself down into the Martian soil. Although if you look carefully, you'll see down in the very bottom, the little pebbles are bouncing around, and they think that's the mole coming back up and hitting the top of or the bottom of the shovel again. So it's not burying itself. We've got troubles with InSight's mole, but that's okay. It's still sending us a Martian weather report. And until Perseverance gets there with all its weather sensors and wind sensors and pressure and humidity and all the rest that it's going to be doing, this is our best Martian weather report we're getting day to day. And you can see here the temperatures are a balmy minus 60 Celsius. That's really cold, everybody. Don't even think about it in Fahrenheit. And then the pressure is incredibly low. That's about 1% of Earth's pressure. But there are some winds. So you're seeing, you know, a 7-8 mile, what is that? A 7 mile an hour wind, if I can see that correctly. So that's our weather report from Mars. But coming to your favorite red planet in 2020 are, like we said, 2 orbiters, a lander, and 2 rovers. So, but Laura, do you think that Perseverance has what it takes to be able to, you know, detect, sleuth out this life? Oh, you're muted though.
It's been a long path getting there. I mean, we've spent decades studying Mars, looking for the right place to go look for life. And so all the orbiters that have done all the global reconnaissance and other landers that have looked in different areas and tried to understand the right mineralogy and the right kinds of geological history that would be conducive. So, you know, we're at that point. We're now ready to start looking for the real deal. And however those cached samples come back, I can't wait to get the answer, see what they find.
Be great to find it.
So yes, when you're looking at up at the sky and you're seeing Mars, you can think about all the spacecraft that are there, and you can think about maybe the microbial life that might be there today. It's not that it may have been there in the past. It still could be there today. So it's a kind of an amazing thing that we can see with our eyes this planet in the sky and wonder whether there are living beings, albeit them microbial, on that world. So yes, this list of missions is just about to get a bit longer. And I love that the names are Perseverance, Hope. These are things we all are needing right now in 2020. And the last, which you mentioned, David, it translates, the translation that I saw is Heavenly Questions.
Mm-hmm.
So it's a name for a poem and that asks these cosmological questions. So hopefully all those missions will give us new insights to our place and among the planets of the solar system. So of course, that our solar system and the inner planets is actually very, very well explored by NASA. If we were to take just a look at the current missions, if you were to imagine, just take a moment before I throw them up there, how many missions are at each of these different worlds, and which do you think is the best studied? So the answer is there. Earth is by far the best studied planet. Sometimes we think of NASA as, only going out there, but in fact, of course, NASA studies Earth in great detail. And our little list of Mars missions has now grown to include 3 more, fantastic 3 for 3 launches, all successful. So we will all be holding our breaths until February comes around, and we hope that all missions successfully go into orbit, land where they want to land, and that they will all start sending back terrific data. So of course, the inner solar system is only half of the story. We have the outer solar system, and as I said at the very beginning, you can see it with your own eyes. Jupiter a little bit closer, Saturn further behind, but also to the east, or to the left when you're facing south. And so just to get a little orientation, remind some of you, in case you haven't thought about it for a while, our solar system's planets are kind of clumped into 2 major groups. You've got the big gassy planets in the outer solar system like Jupiter and Saturn, and the little rocky guys in the inner solar system. And then you have 2 debris fields. You've got the asteroid belt and the Kuiper belt of asteroids and comets, respectively. So that's kind of the basic construction. So now let's play that same game and look at what are the current missions in the outer solar system. Have that in your mind. These are the current ones working now. Oh, it's a little bit of a different story. We've got 2 missions in the asteroid belt that are getting samples. Both are sample return missions, going to bring back chunks of asteroid for us to study in the labs here on Earth. One of those is returning this December. And then there's the New Horizons mission, also in the other debris field headed out, having gone past Pluto and MU-69. But the only planet being studied in detail right now is Jupiter, and that mission is the Juno mission. So just as a reminder, Juno is really there to study the planet. And Jupiter, as I mentioned earlier, is quite a lot larger than Earth, a lot larger than Earth. And usually, though, with the most recent mission that went to Jupiter, wasn't so much focused on the planets as it was focused on the 4 major moons and the other moons as well, but especially these 4 Galilean moons, as we call them, because 3 of them are likely to have oceans inside and could also have microbial life. So there's been a lot of detailed study on the moons, but it's been a while since we really took time to look at the planet. This is a little cutaway. You can see it's a big, big, big sphere of gas with a tiny metallic hydrogen core, nothing like Earth. But the real part that we get to see or our robot proxies get to see, are the cloud tops. And that is exactly what the Juno mission is organized and has as its goal to do. So Patrick, you want to tell us a little bit more about the Juno mission and some of its latest results?
Yes. Well, Juno is very lonely out there, compared to all the other planets that have been studied by other spacecraft. But it's really great to have this space probe going around Jupiter. Juno arrived at Jupiter on July 4th, 2016. So it's been there, going around for 4 years. And it has this orbit where it takes it very close to the planet. And when it's the closest point to the planet is known as perigove. And on June 2nd, it made its 27th pass. And you can see the extent of its orbit. It goes out to about 4 million miles at its furthest, and then goes as close at the perigove to about 2,600 miles just above the cloud tops of Jupiter, and ducking underneath the intense radiation belts of Jupiter. So let's take a look at the pictures that this spacecraft has taken with its camera called Juno cam. So here we have a image that's just taken a mere 3,500 miles away, showing immense detail and a tiny portion of Jupiter. And you can see this red river that's kind of being diverted by some darker material in Jupiter's atmosphere. Very dynamic and incredible detail that you would never see if spacecraft were not to get this close. Let's take a look at another picture. The Juno spacecraft flew again by the Great Red Spot. I think this is like its 4th time, and got some really interesting details of the Great Red Spot. There's also another spot that we're going to circle in the next slide, and this is called Clyde Spot. Why is this called Clyde Spot? Well, let's take a look at the next slide, because this was discovered by Clyde Foster in South Africa using his 14-inch telescope. He was photographing Jupiter with a methane filter, and you see where it says Clyde Spot in yellow. That's his discovery picture. That actually showed up bright in methane. So this was 2 days before the arrival of Juno at its closest point. And so the Juno team was alerted that since the spacecraft's going to fly close to the red spot, let's make sure we have detailed images, high resolution images of what that feature is. So let's take a look at the next slide. And indeed, Juno did photograph the spot. It looks kind of asymmetrical in that visible image picture at top with the great red spot. And then below, it photographed the spot with its methane filter. And in the insert there, you can see the detail of Clyde Spot, which lasted for just a few, I think just less than maybe 2 weeks, and then it just dissipated. Now, in addition to Perigove 27, 53 days later, there was Perigove 28. And here's a really nice view of an anticyclonic oval as seen from roughly about 3,300 miles above the cloud tops of Jupiter. And the next slide, this is going to be a view of the kind of southern hemisphere, showing some of the clouds kind of near the pole, but not quite close to it. There were many pictures posted from us 2028 and of course all the other perigoves. I just happened to pick these two because I thought they were interesting, and picked them as raw images and then image processed them.
So that's right. Patrick just said that he processed them himself. And as I mentioned at the very start of the show, most of the images, nearly all of the images that you've seen from the Juno mission have been processed into these beautiful pictures by just members of the public or interested parties. It's not that there's the official NASA picture that you're seeing. These are always images that have been processed by different people. So we thought, and as I said again at the beginning with the introduction, that we would teach you how to do this, because first of all, it's fun. Second of all, you get some great results. And third of all, some people have a little extra time these days. If you're, going to be staying at home a little bit more and want to pick up a new hobby, a really fun one is to learn how to do a little image processing and process some of these Juno images. So before we show you how to do it, I'm going to just give you a little background. This all comes from a class that Patrick and I taught together. So we're kind of giving you a little insight, like you've come to our class together. So a little background here on how we have seen Jupiter in the past and how have we known what it looks like. Some of you know well that the first real drawings of Jupiter as the planet Jupiter were by Galileo, and no surface features whatsoever. Just he could show the circle. You can see when you look through a telescope back at Griffith Observatory when we're open again, or if you have one of your own, you can see that it's a disk of a planet, not very easy to make out, and certainly not through his small telescope to make out any of the surface features. But over time, things got better, and Cassini, you know that name from the Cassini gap. We won't go, or Cassini division, won't go into that, but he saw the Great Red Spot. He also was able to watch the clouds rotate over time and recognize that the equator rotates faster than the poles in differential rotation. And then in the mid-19th century, just improved drawings and able to track some of the storms. And you can see, again, the red spot was well known. And this wonderful diagram, some of you have seen this wonderful drawing of Jupiter from 1881 with showing the red spot and all the features. So right about that time, photography came into play. And these are some of the earliest photographs taken. As you can see, 1879, 1890. There's that enormous cyclone on Jupiter, the Great Red Spot. And of course, telescopes and cameras got better, but things took a big leap forward when we were able to go there with spacecraft, as we were in the 70s with the Pioneer missions, and later in the 70s with the Voyager missions. And in the 90s, we went back with the Galileo mission. But as I mentioned, it was pretty much focused on the moons. It took a couple of images, and you had to really stitch together the camera, the way the camera is designed. You didn't get those big panoramic or high detail images the way Patrick's Juno images were, but there was a lot of focus on the moon and less on the planets. They did release a little probe that dived into the cloud tops and actually took in situ measurements of the clouds, which is pretty cool, to go all the way to another world and test its clouds. And of course, we've been monitoring the Hubble Space Telescope with telescopes, most notably this Hubble Space Telescope. So one of the things you can see right away from the early 1970s to last year is the change in the Great Red Spot. And if you include the photograph from 1890, you can see how much change. That red spot is really shrinking, and it is almost circular where it used to be very, very elongated. So there's a lot of physics in this, a lot that Juno mission and Patrick has talked in previous times about measuring the heat structure under the red spot and understanding the nature of that cyclone. So that brings us back to Juno, where we have just breathtaking images of storms, of details, cyclones, bands, all of it so beautiful. So we want you to, dare I say it, make Jupiter beautiful again. So just to give you orientation before we go into it, you will be able to find all of this on the Griffith Observatory website. So here on the left, you can see the Griffith Observatory homepage. And at the bottom there are 3 buttons, the rightmost of which says DIY, process your own Juno images. If you click on that, you will come to our DIY process your own Juno images page. And you'll see there's a video there. It's only about 20 minutes, and about 5 of that is just sort of background and information and conversation. So really, it's about 15 minutes of your time to learn how to do this. There's also a very nice PDF. You can open it, read it. It's got step-by-step and to the minute, to the second time codes for each step along the way. So you can always go back and watch how Patrick did it and do it yourself. So yeah, just there's a little close-up of it with, watch the video, download the PDF. And as you can see, it's these very simple things. You just need to download the software, download the images, process them. We'll come to the process them in a second. Go crazy, go wild, let your creative side shine through. and output it. And then the final step, send it to us so that we can post it and share it. You can post it, send it to us in social media, or send it to us in an email, and we will put it on our social media or our website. So Patrick, you want to say just a little bit about where you get the images and just the very rough outline?
Yeah, sure. So what you do is there's a website called Mission Juno. There's the web link up there, and you get to this page called Image Processing, where all the raw images from the Juno missions are posted. And if we go to the next slide, you can see they kind of look bland, but this is a public outreach program. So basically, what you do is you click on any of those images, and you download them, and then you apply your imaging processing. And then what the public has done with this outreach program is that they've took the processed images and reposted them back onto the same page, and you can see all these beautiful colored enhanced images, just like the ones that we just saw from PJ 27 and 28. And that's about what you do, but there is a process to it. So here, what we do is you take these images, you download the raw images, and they come in the red, blue, and green, because that's the filters that's on JunoCam. And there's a map projected images as well, which is basically the red, green, and blue kind of combined together, but not really processed. And then that arrow is what you would do to get them as that beautiful, colorful picture that you can basically repost back onto the Mission Juno site. So, that's about it, but the arrow is the process. So that's the part where you need to watch the video and see how it's done.
And to do that, you would use we recommend in the video, a free downloadable image processing software. So you don't need to even buy anything like Photoshop or anything like that. There's a free public domain open source software called GIMP that you can do all of this with. So all of it's free, easy to get. So we challenged some of the students in our class that we taught to do it. And many of them had never done any image processing before, none. And within just a couple of hours, maybe 3 hours of time, once they kind of followed the instructions and went through it, they were able to put together the images we're about to show you. So the assignment was to just process some images, and then also to kind of turn on their creative sides and output images as well that have more of an artistic impression. So we're going to show you 2 montages of their images, and the first, the processed. These are all museum guides. Some have some processing, some no experience whatsoever. So that was their first assignment. And then assignment number 2 took them a few more hours to make some new ones and add other artistic elements. And we thought these were pretty fun as well. So you too can do that with just a little bit of time and attention. And again, everything, this how-to video here on our website is ready. It's already posted. And maybe if you're a late night owl, you'll stay up late tonight, take a look, or perhaps tomorrow when you're thinking, oh, I can't go anywhere and I can't do anything. Well, yes, you can. You can do something you've never done. You can make beautiful images from Juno. So with that, I would like to invite Jeff McKibben to come into the room because we will be hearing our next story from Museum Guide Jeff. Jeff, you didn't take that class, so we don't have any of your fancy artwork, do we?
No, we don't. That's okay. Well, now that you've all learned how to make beautiful images, let's talk about death and destruction. We're going to talk about the Cretaceous Paleogene extinction, or what many people know as how the dinosaurs died. This is a pretty expansive field of study, and it's much more recent than a lot of people realize. What we now know as sort of common knowledge as the way the dinosaurs died was originally called the Alvarez hypothesis, named after a father-son team who posited that, hey, these dinosaurs and all this other life probably went extinct because of a giant impact. And they saw evidence of this down south in Mexico, right off the Yucatan Peninsula. If you look at the little map on the lower left, you can see there's actually a ring of sinkholes forming an oddly well-formed circle. And then on the right side, on that same map, you can see under the surface, there's evidence there used to be an enormous crater there. So this led people to thinking, well, yeah, okay, this impact that happened the same time the dinosaurs went extinct probably had something to do with it. But this is not the only hypothesis that's been recommended. That's right. There is a contender. Who really killed the dinosaur? Was it Team Impact or this new challenger? And this new challenger is Team Volcano. Specifically, we're talking about the Deccan volcanoes, which if you go down, if you look, on the right side, you can see these huge steps are a formation called the Deccan Traps, and they're still around in India today. They actually take up a pretty large chunk of India. The Deccan Traps are in the red there, and they are all of these flood lavas that have solidified. So the amount of volcanism that it would take to make these enormous lava flows, people got to thinking, well, hey, when did these volcanoes even erupt? Does it match up with the dinosaurs? And yeah, it turns out that there was Deccan volcanoes erupting pretty continuously for about 1.5 million years before the dinosaurs went extinct. So this got scientists and some of the general public to thinking, well, was it the asteroid? Was it the impact? Was it the volcanoes? What really killed the dinosaurs? Or was it some combination of both? And some research came out earlier this year that was actually very cool. It used climate modeling software, what's called an AOGCM, to figure out what happened to the Earth's climate after the dinosaurs died. This kind of model has been used a lot in modern climate modeling. At the IPCC, the Intergovernmental Panel Climate Change, they use these models a lot to try and figure out, all right, well, if we increase or decrease emissions, how will the climate go? A lot of what we know about climate change is from this kind of modeling. But there's kind of been a problem with these kinds of models in paleontology, is that a lot of these that have looked at the Cretaceous extinction have used a map like this, which is the modern day arrangement of our continents. Now, this is not a good idea because the position of the continents affects how the ocean currents, how the air flows, where precipitation lands. It can affect lots of different things about the Earth's temperature, rainfall, and climate. So what this team decided to do was they said, all right, well, we know the continents have moved over time. There have been so many simulations showing this, like this next one from Dr. Scotese, he has a YouTube channel with so many good little simulations, but it shows that the continents have been moving and are still moving. So what this research team did was they said, all right, cool, we're going to take the highest quality end Cretaceous map that we can and run a climate model on that. And so they did. They said, no, we're not using this map. Get it out of here. It turns out there was some actually previous studies that have used this. One of the authors on this study was on sort of a smaller resolution study, but this one was better. This is great. So they set out to finally answer the question, who killed the dinosaurs? Impact or volcanoes? And they found that it was the impact. It turns out the Alvarez hypothesis holds up even after all these years. And the simulations themselves are actually pretty interesting because they found a little extra information. What they modeled was they modeled how the climate was at the end of the Cretaceous. So on the left side, you can see the world's temperature, with red being hot, blue being cold. And on the right side, you see precipitation, which is either rain or snow or water falling from the sky in any way. Purple being more, green being less, white being the least. And they found what we would expect. After the impact happened, there's what's called an impact winter. And this is after, of course, the immediate giant firestorm and tsunamis and all of that. But this impact winter has a bit of a longer term effect. So you can see it got much colder and much less precipitation fell. But then they decided to factor in, okay, cool. What if we throw in the fact that volcanoes have been continuously erupting for the last 1.5 million years? With all the extra CO2 from those volcanoes, they went ahead and they ran the models again, and they found that, hey, the temperatures are warmer and there's more precipitation, which is actually great because both of these things are very important to life. There we go. So with a more habitable Earth, because these volcanoes had been going on for a while, they came to the conclusion that not only was it the impact that killed the dinosaurs, not the Deccan volcanism, but that the volcanism actually had a positive impact on life. So there you see our volcano character carrying some little critters to safety. Who knows what life is alive now that might not have been if it hadn't been for those volcanoes.
Well, you can see the little tiny mammals, which are our great to a many.
We'll just keep on saying great for a couple of hours and then
that'll keep everybody entertained. And of course the poor little dinosaur coming out of it, he's not gonna make it. Very, very sad. So thank you, Jeff. I wanted to comment, oh, well, he's gone now, but that with all those moving continents, it made me think about the earthquake I think everyone, if you're watching from Los Angeles and you set your alarm to get up and watch the Mars launch, yeah, who needed an alarm? That was continents moving that caused you to wake up just prior to the Mars launch. That was a crazy, crazy morning. So anyway, moving on, another way to escape perhaps a devastating circumstance in Earth's environment. If we don't have a nice volcano character to carry us away to safety, another way to find safety is to make us a multiplanetary species. And so this next story is all about that, about human spaceflight. Everyone watching is aware that we have sent astronauts to the moon, and that the moon exists, and that the Earth is round because the astronauts orbit it every day, every 90 minutes. And so we've had astronauts going into space since the early 60s. We've had a setback in US launch capability after the shuttle was retired, and we have been dependent on the Russians to carry us to the International Space Station. Well, in May, of course, we had a big news in that we had a launch of a vehicle built by SpaceX of these two marvelous astronauts, Doug Hurley and Bob Behnken, otherwise known as Bob and Doug. And so you always just have to, if you have any Canadian friends or relatives, of course, that's the first thing you think about. But no, these two didn't go. Bob Hurley and Bob Behnken and Doug Hurley went, launched beautifully in the end of May. For those of you who watched it, you know it was really kind of nerve-wracking because it's a new vehicle and it's flying people, and if anything goes wrong with it, we've got some problems. Of course, they had done all the testing and they felt ready. And sure enough, beautiful, flawless, perfect launch. The astronauts had about 19 hours in that vehicle as they flew up to and rendezvoused with the International Space Station. We talked about it then. There's a ton of really interesting things in this Crew Dragon capsule built by SpaceX. But the key thing is that it did successfully
2 meters.
Join the International Space Station, carried the astronauts
We're
up
inside the
and
hands-off point, the chop
docked
crew
with
hands-off
the
point.
International
1
Space
meter.
Station. And sure enough, and I'll just cut right to it, Bob and Doug were able to join the other astronauts already aboard the International Space Station. And success. Very, very exciting. I'm sure you all saw that. So that was about 2 months ago, and that's where Bob Behnken hits his head as he's coming in. I understand it really hurt for a while there. But they were on the International Space Station for 2 months, and I know they did some spacewalks. And David, did you get a chance to look at some of that, or shall I? Yeah, David, can you tell us?
Yeah, I did. They brought some stuff with them. A new equipment bay to do experiments in. They did some water droplet experiments. It looks like they were also tasked with just sort of installing a lot of the equipment that was brought with them and to set up. So they were used in sort of I don't know, an all hands on deck sort of a way. So the water droplet experiment I thought was super cool. It actually was a shower head of sorts to look how those droplets form in 0G. So they did do some cool work while they were up there. Fun times.
Great.
Yeah, in the press conference, they were saying they were so busy because they were filling in for because they only had a small amount of crew, so they were filling in for all the maintenance work that the other crew, fully crewed space station would actually do.
So it's great. You guys are making history, brave astronauts, but as soon as you get up here, it's time to swab the decks.
Yeah. Grab a wrench and start, tightening things down, install the equipment bays. There was a robotic tool bay as well that it's going to store the robotic tools, which is robots up there doing stuff. They got to have a place to put them so they don't float away. So
great.
Neat.
Well, the big news was that last week it was time for them to come home. And so let's see here.
And we have motion.
There we go.
You see Dragon
barely discernible
from
when you're
Space Station
undocking or docking with the International Space Station. You do it very, 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 very slowly because you don't want anything to bump or hurt or crack anything, obviously. So they had a beautiful and successful undocking, and then again traveled for 19 hours while they had to readjust their orbit and have a final burn so they could splash down in what turned out to be the Gulf of Mexico. There were several possible landing spots, but that was Hurricane Isaias was along the Florida coast on the Atlantic side. So they opted for the Gulf of Mexico landing spot, and here's how it went.
Standing by for splashdown.
Don't know if you're hearing the sound. The big cheers. You can see the what they call the fast boats. You know, back in the Apollo era, which was the last time I saw a splashdown, it was U.S. Navy carriers and U.S. Navy ships. No, these are also SpaceX assets. So it was NASA astronauts on a SpaceX vehicle, but all of this recovery, all of that was done by SpaceX. So here are just some shots because it's such a magnificent success and everybody was so excited about it. They're pulling the Crew Dragon out of the water and onto the deck of the ship. And then next step, open the hatch. And what was inside, our astronauts, Bob and Doug, happy, healthy, everything was great. Now they'd been in space for a couple of months, so didn't have their Earth legs. They got carried out, and then here they are finding their way back to the mainland and to their families, and to, well, I should say, and first to the press conference, because you got to do that first. So both of them, great, both of them very excited. So I've had 3 clips, and I am not hearing sound. I would love to know if we are getting sound on the feed. because these are 3 clips of Elon Musk speaking. And okay, great, thank you. The first, well, it speaks for itself.
Thanks, Jim. I mean, after these great words that were spoken, I'm not sure I have much to add. There's from Bob and Doug and Jim, but I do think what this heralds really is fundamentally a new era in space flight, a new era in space exploration. We're going to go to the moon. We're going to have a base on the moon. We're going to send people to Mars, and make life multiplanetary.
So back to that multi-planet species, something that you've probably heard him say before, about which he's exceedingly passionate. It's sort of the reason to be for SpaceX. Very inspiring words. He was also kind of blown away to the point of being sort of speechless, and it was kind of fun to watch him express that enthusiasm.
I mean, I really came here because I just wanted to see Bob and Doug, to be totally frank. It was like, oh, thank goodness. I think like my entire adrenaline, it was just dumped, you know. It's like, thank God, you know. And I'm not very religious, but I prayed for this one.
So I like that. You didn't really, I don't remember seeing the administrator of NASA go after we launched astronauts from the moon. It's a different era. And then this last one I like because I think we can all identify with some of what he's saying here.
Thanks again. And, you know, I think this is something that the whole world can take some pleasure in, and can really look at this as an achievement of humanity. And there's, you know, these are difficult times when, you know, there's not that much good news, and I think this is one of those things that is universally good, no matter where you are on planet Earth. This is a good thing, and I hope it brightens your day. Thank you.
So I had a lot of family and friends say exactly that you know, boy, wasn't it great to feel great about something and to be able to celebrate globally a really wonderful achievement. So congratulations to Bob and Doug and to SpaceX. But SpaceX, being SpaceX, had other things going on. In fact, this test I'm about to tell you was scheduled for the same day as the splashdown, and they thought, well, we're a little busy today, so they pushed it back a couple days. But you might be aware of the SpaceX vehicle called Starship. That is the one that will carry passengers to the moon and eventually onto Mars. Will land vertically on Mars, just like the old movies, and astronauts will disembark on the surface of Mars. So it was rolled out not too long ago. This was just a mock-up. But then they've been trying to run some tests to see the thing get off the ground and land. And some of you may remember this test from the last All Space Considered. Yeah, that went really well. So it's always fun to watch the fireball, but I might just keep moving in the interest of time. Yes, it was all in flames, and when the smoke cleared, this is what you got. Not very good shape, that vehicle. But as Tony said, because Tony covered this story last time, they already had the next one in the bay being built, even as the wreckage was being carted off that pad. So that one being built was the attempt to have it rise and then land vertically. Just happened, was that Tuesday? I'm sorry, I should have had that in my head, just this past week. And here we go. then it sank back into the cloud of smoke, so you couldn't see whether it was safe or not. But you listen to them, listen to the crowd going nuts and saying, "There's no big boom, there's no explosion."
We're good. That's got to be good.
Come on.
Let's see.
So this feels like
That's
an
gotta be good.
eternity.
We're good.
It feels
It's quiet.
even more like an
It's gotta be
eternity
good.
for those folks
Show me.
waiting for the smoke to
Oh my
clear
God.
to see if it
Show
was
me
standing
yes, I
upright
want.
where it
Where's
had
it at?
landed.
It's good.
Oh my God.
And indeed it had. So huge step in the right direction for SpaceX and their I just said it a minute ago, I'm blank on the name. Anyway, so it's a great step in the right direction to that day when these Starship lands on Mars, carries us to Mars. So with that, Patrick, our last story in the first half before we go to break and have Katie join us. Can you please tell us what's in the sky this month?
Yes. So, well, we're going to start with this image. I took of comet Neowise, which was an unexpected visitor back in July, and it became naked eye in the morning sky and then in the evening sky. This was taken July 18th when it appeared in the evening sky. Now, since then, if you were to try to find it and go to the next slide, we'll see that it has faded from its former brilliant glory into an object that can only be viewed through a pair of binoculars. So currently, if you go out tomorrow night at 9 p.m., if you want to see it, it's going to be located in the constellation of Gamma Berenices, just below the bright star Arcturus, which is right above it. Now, on the same night, with that little smiley face, if we follow the arrow to the left, we'll face south. And in the southern part of the sky, roughly about 9 o'clock, our sky is dominated by the constellation Scorpius, the Scorpion, with its red star Antares, which actually looks similar to Mars and is known to the ancients as a rival of Mars. So you might catch a glimpse of that in our summer evening skies. And of course, we mentioned earlier, the two bright planets, Saturn and Jupiter, are visible in the southeast, and they'll be up throughout the month and throughout the for the next few months. So please go out and take a look at it if you haven't seen it, or if you've already seen it, they are kind of a sight to see. Now, if you were to stay up just before midnight tomorrow, make sure you look to the east and catch a glimpse of the rising moon, and just right above it is the planet Mars. And so they're very close together. They're roughly separated by less than a degree apart. So that's something worth looking for. And the next day, of course, the moon will move away, but it's neatly parked underneath Mars for tomorrow night. Let's go to the next slide. Now, August is the time to go out to watch meteors. If you're going out camping to a dark sky area, or even if you're still in the city, you're sure to see a few meteors from this particular shower. It's Perseus, and the radiant is located just above the constellation of Perseus. As you look to the northeast, you look at the next slide, you can see the location. There it is. And this view is set for just about 10 o'clock tomorrow, but Perseus will rise higher and higher as the night goes by. It is the peak time, so next Tuesday, the night of the 11th through to the morning of the 12th. Look between the peak time between 3:40 to 4:40, and the expected dark sky rate is roughly about 95 meters per hour. Just be aware that the moon will rise at 12:22 and will hamper your view of some of the fainter meteors. Best way to go out to see it is take a lawn chair, lie back, look straight up, and let your eyes get dark adapted, and you should see a few meteors, maybe one per minute. Now we're going to go and take a look at this view here. This is a morning view on August 18th, and the moon is just above the planet Venus. To the right is the beautiful constellation of Orion, just coming up early in the morning in our summer skies. Next slide, please. And we're going to take a look at the moon phases, and so you can see that on the 11th is last quarter, the 18th is see here is new moon, and first quarter is the 25th. We're going to leave you with this view here. This is at the end of the month where you can see all three planets and the moon together. And if you were out on a stroll in a summer evening on the end of the month, 10 o'clock, look for Mars in the east, moon in the south, in the southeast, and in the south, of course, are two giant planets in our solar system, Saturn and Jupiter. So hope you go out and take a look at these and make sure you catch the Perseid meteor shower.
Thank you, Patrick. Now comes that time of the show and of the evening where we invite you to dim your lights, and we're going to show you a couple pretty pictures. It's always nice to just take a moment and enjoy the beauty that nature has to give to us. We will go from pretty pictures into 2 break videos. Each is about 5 minutes. So we have about 10 minutes. As I said earlier, that gives you a chance to go refill that glass of wine or whatever it is you might be enjoying. Take a powder, go outside, take a quick look at Jupiter and Saturn, and then come back and join us for the second half when we have our guest Katie Mack joining us. So with that, I hope you've all turned down your lights and you're getting all relaxed, and we will move forward with our pretty pictures. So. That's a timed and stacked image of the annular eclipse that we had, annular solar eclipse from just a little over a month ago. These last 2 are taken by museum guide David Pinsky. And this in particular, kind of awesome. He actually captured the International Space Station with his Canon camera. So. Okay, welcome back to the second half of All Space Considered, and we hope you enjoyed those beautiful images while you were seeing and listening to that lovely music and taking a little bit of a break. We're very excited to have a special guest in the second half, and we'll come to that in a second. But while I had a moment of break, I went, because I meant to have this in the first half, and found my Jupiter face mask here that's got the holes and everything, but you can see, yeah, lovely picture of Jupiter. So, you know, there's all kinds of fun astronomy stuff to put on your face since you're all wearing masks and keeping everybody else safe around you. So I thought I'd share my Jupiter one. So with that, I want to welcome our guest, Katie Mack. Come in. Yes, please do. Come on into the room, Katie. And Katie has just recently written a book called The End of Everything, Astronomically Speaking. So we are, in keeping with our cheery Armageddon themes from the first half of the show, we're going to just talk a little bit further about not just the end of the dinosaurs or the end of humans on Earth, but the end of truly everything. So with us, we have a wonderful expert, cosmologist and Professor Katie Mack from NC State. Katie actually had an early passion for astronomy growing up here in Los Angeles and came to Griffith Observatory as a young girl and young woman, and went to Caltech, so very local. And but she is now, well, actually she's right now in Toronto. I think, Katie, you said you kind of got stuck there. You were in Toronto and then suddenly you weren't going to go anywhere.
I was in Waterloo, Ontario, just a little ways outside of Toronto, at the Perimeter Institute for Theoretical Physics, where I was doing a 6-month fellowship. But now I'm actually in Massachusetts for complicated reasons. So I had to leave Canada because my visa was up, and it's been a strange time. But I'm just doing my work remotely as a theorist. That's very easy to do. So. Now I'm in Massachusetts doing the same thing, you know. And
we noticed the blackboard behind you. You want to what's that all about?
Yeah, so that was a gift from Perimeter Institute. I used it first for a public lecture I did with them, one of these online public lectures, and they wanted me to be able to draw stuff during the talk, and it turns out it's really useful for supervising students. So I have a research student I've been working with remotely during the summer, and I write my equations on there and talk to her, and it works much better than any kind of complicated technical annotate screen solution. So it's a very helpful thing to have.
It's like Battlestar Galactica, right? Use the lowest tech.
Yeah.
But it's very reliable. I understand.
It is.
So what drew you into astronomy here in Los Angeles when you can't really see the sky?
Yeah. So a lot of my colleagues in astrophysics, they got into it through stargazing, through falling in love with the night sky, and in LA that's difficult. I did go to the observatory a lot. My mom used to take me up to Griffith Park from time to time when there was a comet or an eclipse or something like that. And I did join the LA Astronomical Society at some point, and went to the dark sky star parties when I could. But mostly I got into astrophysics through the physics side, through trying to understand what I could about the universe, getting excited about black holes and the Big Bang and space-time and all of that kind of thing. I used to go to public lectures and read books by Stephen Hawking, and I really fell in love with that, all that mind-bendy physics.
So with all that mind-bendy immensity out there, what made you decide to talk about the end of it all?
Well, I've been doing cosmology for a while and studying a number of different things, including early universe physics and dark matter, and a lot of times when I'd give public talks, I would talk about kind of what what we're learning about the evolution of the cosmos and stuff. And at some point I started to include some things about the end of the universe in the talks I was giving. And I was hearing some really interesting new research around certain end of the universe scenarios, and I would include that as well. And people really got excited about the end of the universe, and that was always a big kind of crowd pleasing thing to discuss. And so I thought, if I'm going to write a book, there are a lot of books out there about the beginning and not that many about the end, and it seemed like a nice way to introduce people to some cool cosmology topics, and to help people get an idea of where things stand in cosmology, and what we're thinking about in physics around that question. Because the ways we think about the end of the universe have changed a lot in the last few decades, and I wanted to help give people some access to that information. And it was just it's kind of a fun, slightly scary topic, and people enjoy that sort of thing. So.
Well, why don't you tell us a little bit about the book, and tell us a little bit about the ways in which all of it may end?
Yeah. So the book is, it goes through 5 different possibilities for the end of the universe. And they're not necessarily the only things that could happen, but they're the ones that are kind of the most discussed in the literature, the most likely based on, or not necessarily likely, but the most seriously talked about by professional cosmologists. And they represent a range of possibilities that kind of illustrate where things could go if the data look just a little bit different, or if the theory is tweaked just a little bit. So it's a nice kind of overview of some fun possibilities. And so in the book, I start with an introduction to just the field in general, and then I go through the Big Bang to now to get everybody on the same page, and then I go through destroying the universe for several chapters, and then talk about how we're figuring it out, and what kinds of tools, new telescopes and experiments and advances in theory we're going to have in the next few years and decades. And then I have a little epilogue that's kind of like, okay, we've been through some stuff. Let's talk about how we feel about this, and I include a bunch of quotes and discussions with other cosmologists, because when I was researching the book, I was going around talking to colleagues about, where they think the field is going and such. And I made sure to always ask the question, so how does the end of the universe make you feel? And I got a lot of different answers. And so that was really fun and interesting to hear how people who are actually studying this day to day feel about the prospect of the universe coming to an end. And it wasn't all the same response. There were some people were totally fine with it, some people not at all, and that was very interesting to see.
Great. Well, do you have? I understand you have prepared a few visuals to help share some a little more in depth with this.
Yeah, so I thought I would go through 4 of the 5 scenarios just briefly to give a kind of overview of what these things kind of look like. And then, I won't go into any detail on these, but just to give an impression of kind of where things stand. So I'm going to try sharing my screen, see how this goes. Let's see, okay. All right, so hopefully you can see my screen there, my title slide. Okay. All right, so yeah, so this is just a sort of brief talk about how the universe ends, a few different possibilities for that. So, okay, so the main idea here is to think about the cosmos as a whole, and where things might go in the future, what we can expect to happen, and is it really just going to kind of dissipate and go away and be destroyed completely, or what should we really look for? So in this case, the 4 that I talk about are the Big Crunch, heat death, the Big Rip, and vacuum decay. Now in the book, there's an extra one, a bouncing cosmology, and we can talk about that more later, but for the purpose of this, you get the first 4. So starting with the Big Crunch. Okay, we are here, we're in the Milky Way galaxy. This is a nice view of the Milky Way galaxy from Southern Hemisphere, where you can see the center of it, which is very cool. And if we were to be outside of our galaxy, it would look something like this. We're kind of on the edge, somewhere near the edge of this spiral galaxy. And our galaxy has somewhere around hundreds of billions of stars in it. And we see galaxies all across the universe, and we can see them out to extreme distances. And when we look out into the distance and into the past, we can see galaxies that existed during the first few billion years of the universe. And we can see that what we see when we look out into the cosmos is that galaxies are moving away from each other. They're moving away from us, so we see them as though they're moving away from us, but they're really every sort of well-separated galaxy is moving away from every other. The universe is expanding. And so for a long time, there was this question, will the universe continue expanding forever, this expansion that was sort of kicked off by the Big Bang? Or will the gravity of all the things in the universe start putting the brakes on that expansion, pulling things back and causing it to recollapse? And so if that were to happen, what we would see is that the galaxies would start coming back together. This is my very sophisticated animation of this. And we would start to see that instead of galaxies all receding from us, they would be approaching. And so we would see them getting closer and closer, and the universe would be getting denser and denser. And at that point, we would see more interactions between galaxies. And no, we do see that a lot in the sky now. There are places where galaxies are colliding with each other, interacting. It gets very complicated. But that's not really what is dangerous about a big crunch cosmology. So it's not that galaxies smash into each other and everything kind of breaks apart like a car crash. The thing that's dangerous about a big crunch, about the universe contracting, the thing that really kills the stars, is that when the space is compressing and all of the galaxies are coming together, it's not just the matter that's compressing, it's also the radiation. It's all of the light, the background light that's been in the universe all this time, and also the starlight that's been shining for all of these billions of years. And so if you are a star hanging out in the universe when the big crunch is coming, the thing that kills the stars, and this is the coolest thing about the big crunch, so I'm giving a little bit away, but you might appreciate it. The thing that kills the stars during the big crunch is not the stars crashing into each other. It's the fact that the ambient temperature of empty space, the amount of radiation that is being compressed into a smaller space during the big crunch, it gets to a point where it's enough to ignite the surfaces of stars and cause thermonuclear explosions all across the surfaces of stars. And that's what kills the stars. And I think that's fantastic. And of course, at that point, nothing survives. So it's a kind of scary story. That bit was first worked out in the late 1960s, and was a very scary thought. That at that time, that seemed to be the way things were going, that we were going to head for a big crunch. And now we don't think that's going to happen. More likely is the heat death. And this is the one that is thought to be, probably what's going to happen to our universe. So the heat death starts the same way as the big crunch. The universe is expanding, but instead of the expansion stopping and turning around, it continues. And in fact, now we know not only is the expansion continuing from the sort of initial kick of the Big Bang, but it's also accelerating in its expansion. The expansion of the universe is speeding up. And we don't know exactly why that is. There's whatever's doing that, we call it dark energy. It's making the universe expand faster. It might be a cosmological constant, which is a sort of just a property of space, that space has this inherent expansion in it. And if that's the case, then over time, there's more space. And so there's more expansion of space. And the matter that should be sort of putting on the brakes on this expansion gets more and more diluted. And so the expansion just keeps accelerating and accelerating. And what that does is that it just increases the empty space and everything gets more and more isolated. And in this scenario, by around 100 billion years from now, our little group of galaxies will be totally isolated from the rest of the universe. We will not be able to see distant galaxies anymore. And each galaxy or little group of galaxies, if they're already kind of in a clump to begin with, will be more and more isolated, and there won't be these grand galaxy collisions that could bring in new gas and form new stars and everything. And so the stars that exist in each of these galaxies will kind of burn out and fade away, and matter will decay and black holes will evaporate, and over time the universe ends in this cold, dark, quiet, empty space. And that's called the heat death of the universe, when there's really nothing left in the universe except a little bit of trace waste heat from all of the processes that ever occurred in the cosmos. So that's a bit of a sad story, and not a particularly exciting one. The next one's a lot more exciting, and we can't entirely rule it out. So the next one starts the same way as the heat death. The universe is expanding. It's speeding up in its expansion because of dark energy. But there's an extra piece of this picture in the scenario of the Big Rip, because in the case of the heat death and our sort of usual idea of the accelerated expansion of the universe, the dark energy is able to pull galaxies away from each other because there's a lot of empty space, and anything that's not sort of already bound can be separated because there's more empty space in between. But if dark energy is just this cosmological constant, just this property of space, it doesn't affect the galaxies themselves. It doesn't like try and unravel those things. If there's already a gravitationally bound object like a galaxy or a solar system, it's fine in that picture. But the Big Rip is what would happen if dark energy were something more violent, if dark energy were something that kind of got more powerful over time. And then not only was it able to move galaxies apart, but also to kind of pull the stars away from galaxies, to pull planets away from their stars, to pull apart eventually all of matter itself. And that would destroy not only all the structure in the universe, but at some point kind of tear apart space completely. That little animation there that I just did, I did that in Keynote, but a few years ago, NASA made an animation of this to illustrate the idea of the Big Rip, because depending on how you look at the data, certain bits of the data might prefer this a little bit over other possibilities. And I just want to show the NASA animation here because I think it's really great. So here we go. The expansion begins, and then, oh no, the galaxies are torn apart. Oh, yeah, I gotta watch that again. So the thing about the Big Rip is we can't necessarily say that it won't happen, because the difference between the kind of dark energy that gives you a heat death and the kind that gives you a Big Rip, it could be very subtle. So there's a measurement you can do having to do with what the dark energy is, and if you get a certain number on that, then you've got cosmological constant. If you get a number that's any little bit smaller than that, then you get a Big Rip. And so all we can really do is say, we have at least about 200 billion years before it's remotely possible for a Big Rip to happen. So that's where we stand with that. Although if you ask the theorists, sort of me, but also other theorists, the Big Rip is less. It's sort of a less appealing idea in terms of the theory. Which brings us to the final one I'll talk about today, vacuum decay. So this is my personal favorite because it combines some cool ideas in particle physics with universe-ending cosmology in a really fun and interesting way. So a few years ago, the Large Hadron Collider was able to find kind of the final piece of the standard model of particle physics by discovering the Higgs boson. So this is a picture of an animation of a cartoon of an event display at the Large Hadron Collider. This is a machine that swirls protons around in an accelerator and smashes them together to see what comes out. And the point of doing that experiment is to examine the forces of nature, the fundamental particles that make up everything. And when the Large Hadron Collider turned on or found the Higgs boson, it completed the standard model of particle physics. So this is an illustration of the standard model of particle physics with the Higgs boson up there. And what we have here are, we have the quarks, which are the particles that make up the centers of atoms, protons and neutrons. You get 3 quarks each in protons and neutrons, and the other quarks are just related particles. There's the leptons, which include the neutrinos, which go through, they're produced in the sun and they go through the earth all the time. There's the electron and its cousins, the muon and tau particles, the electron being what goes around the nucleus of atoms, or if you're looking at it in a quantum mechanical way, it's a kind of haze of electronness probability ball around the centers of atoms. And then on the right on this picture, we have the gauge bosons, which are the force carriers, the things that mediate the forces of nature. So there's the photon that does electromagnetism and light and magnetism and electricity, the gluon that holds particles together inside the centers of atoms, and the gluon does the strong force, the strong nuclear force, and then the W and Z gauge bosons, which are they have to do with nuclear like radioactive decay and things like that. They mediate the weak nuclear force. The point of showing this is that these are the particles we know about. This is the standard model of particle physics. It matches all the data we've ever gathered in particle experiments to a pretty good precision. There are a couple places where there might be little anomalies. At some point we had to revise the mass of the neutrinos from 0 to a little bit more than 0. Basically, the standard model of particle physics works. And one of the things that it can tell us is it can tell us something about how stable physics is, how stable the universe is. Like, is this sort of configuration of particles and fields, does this really work in the long term, or is there something slightly off about it where it could collapse into a totally different configuration of particle fields that would be bad? So you can take a few of these particles, the top quark and the Higgs boson, and you can do some measurements around those, and you can make a plot of regions of stability or instability or metastability. I'll explain that in a minute, for like the universe, for how physics works, where in this plot, the mass of the Higgs boson is on the x-axis, the mass of the top quark is on the y-axis. And so, for example, if the Higgs boson had a mass of 50 GeV and the top quark had a mass of 50 GeV, then you'd be in this nice stable region where everything's fine and the universe and physics work fine forever and you're good. So finding the Higgs boson and measuring its mass gave us important information about where we sit in this parameter space, what our universe is really like, right? And when that measurement was done, we found that we live right there. So that's the metastable part of the plot, which means that the universe is stable for now. And specifically, it means that there's a kind of vulnerability built into how physics works in this universe, where something could happen that could change the laws of physics at one point in the universe and create a catastrophic cascade of a different kind of space. I'll show you what this looks like. So what would happen is we have this Higgs field, which is this sort of energy field that pervades all of space. And at one point somewhere in the universe, that Higgs field would undergo a quantum transition where it would change its value, which would totally restructure all of physics and create a bubble of a different kind of space, where inside this space, the laws of physics are different. The standard model is not the standard model anymore. You have different particles, different fields. And if you were in that space, the constants in nature would be different. Your particles wouldn't hold together anymore. That would be bad. And this bubble, it's called a true vacuum bubble. This bubble would be expanding out at the speed of light, which means that if you're standing nearby, then you will not be able to see it coming. There is no possible way you will know that this is approaching you as it's occurring. And what it would do to you is it would first, the bubble wall would come and and sort of incinerate you, and then you'd be inside this bubble where your atoms wouldn't hold together, and then it turns out after that you would collapse into a black hole. So clearly that's
glorious death. You know, we all becoming black holes. That's kind of dramatic.
Yeah. So clearly this is something we want to avoid, and there are a couple of things I always say about this. One is that because this is a quantum tunneling event, we can't predict when or if or where it would happen. All we can say is that there's, the probability is that it almost certainly would not happen for the next, 10 to the power of 100 years or something like that in our observable universe. On the other hand, we can't say for certain, but there are a number of reasons we shouldn't worry about it. One is that, there's nothing you could do about it. You wouldn't see it coming. It would be totally painless because it's happening about the speed of light and your nerve impulses don't travel that fast. Nobody would miss you. There's no tragic aftermath. But also, the idea that this can happen at all is based on the standard model of particle physics being completely reliable. And we know that it's not. So if we look at what the universe is made of, we know that the universe is made mostly of dark energy, which is the stuff I mentioned before, where we don't know what it is. We don't know how it's going to act in the future. It's made, after that, most of the rest of it is dark matter, which is some invisible matter that holds galaxies together, but we don't know what it's made of. It's not something where we, can say, well, it's that kind of particle there. And then there's about 5% of the universe that's all of known particle physics. The entire standard model of particle physics is in there. So if we're trying to make an inference about what the universe is going to do in the future, and we're basing it on this little tiny 5% slice when there's 95% of the universe that we do not understand, we're bound to be missing something. So in my work and in the work of other cosmologists, we're putting a lot of energy into trying to understand that 95% of the universe, that's the invisible, mysterious stuff that's driving the evolution of the cosmos. And maybe once we figure that out, we will find entirely new fates for the universe, entirely new ways that our whole universe could evolve and change and potentially, come to an end. So that's the end of my presentation. So I will turn this off.
Before you turn that off, oh well.
Yes.
Yeah, well, you're still there. Could you go back to the slide with the mass of the top quark and the mass of the Higgs boson?
This one?
Yeah.
Yeah.
Before you put the dot up there, I was thinking to myself, okay, what does it need to be where any of the four possibilities could be true? And lo and behold, that's the mass of the top quark. I mean,
it is weird that we're right there.
Yeah.
Yeah,
really,
yeah.
We didn't know Higgs boson, any of those were possible until, was it 2012 or whenever that was?
Well, I mean, we couldn't have been, if we were in the instability part, our universe would already be dead. So that part was basically ruled out. But yeah, I mean, it was kind of assumed we'd be in the stability region before this was discovered. And if you talk to particle physicists, some will say like it's weird enough that we're right on that edge, that we're just barely not in the stable region, that this must be telling us something profound, that we can't really be metastable, that there's the idea that the universe really is in this state where where the expected lifetime of the universe is more than the age of the universe, but not so much more. That seems suspicious, right? And
the critical density, the ratio of the observed density to critical density is so close to 1 that it must be, I mean, it just has to be because it's so close. And it sort of has that same feel. You're right on that border. And in
I mean, yeah, if you zoom in a bit, we're not that close to stable. It's but it's a fairly small part of the parameter space that we're in. So it does seem like we're like, it's only, you don't have to be that wrong on the measurements to make us actually stable. So maybe it's telling us something deep that that there's some small correction factor that we haven't figured out yet. And if you talk to different physicists, you'll get different answers. I was talking to one last summer who was saying like, well, maybe we've just been lucky so far. Maybe, we don't know what the real time scale is on this transition. Most people would say that it's the time scale is so long, it's not something that's going to be a factor for how the universe evolves. But particle physicists are taking this seriously. I wrote a paper about this stuff because I find it fascinating. It's a real topic of research, and it's a really interesting possibility that that the universe just might not be fully stable. There's some other state of the configuration of physics that is preferable in some way, and if you tweak our universe in just the right way, we will revert to that unlivable space.
That's remarkable. Why don't you come on back in the room, shut down the sharing so we all have a bunch of questions. I know one I want to ask right off the bat is, and it ties to this question about the measurements being so close. I mean, do we really know the mass of the Higgs boson that well, or could we be? Yeah. So I do want to ask the theorist some observational questions, but you mentioned that as a critical measure. You also mentioned a measurement of the dark matter as being a critical. If it's low enough, then you are in the big
dark energy.
Oh, pardon me, the
dark energy.
So tell me about these measurements. Are they on the horizon? Are we going to get answers to that? Any refinements? How are we going to know?
Okay, so with dark energy is a really tough thing to study because all it really does, as far as we can tell, is make the universe expand faster. It seems to be totally uniform through space. It seems to be acting the same, through time, as far as we can tell. We haven't found anything different about that. It's invisible. We can't touch it. Experiments don't seem to be able to do anything to it. So what we can do is we can measure the expansion rate of the universe at earlier times than today. We can see how the universe has been expanding, the expansion history. And we can measure how galaxies and clusters of galaxies and so on have formed throughout history, because that's been influenced by how the universe is expanding. So those are the kind of the measurements we can do. And so far, all of those measurements are consistent with the idea that dark energy is just a cosmological constant. It's just something that is a property of space. And the reason the universe is speeding up now when it wasn't speeding up before. So the universe was slowing down in its expansion for about 9 billion years, and it just started speeding up in its expansion about 5 billion years ago. The reason that's happening is because there's some constant amount of dark energy, constant amount of cosmological constant. The density of this stuff, whatever it is totally constant. And that means that in the early universe, when the density of everything else was really high, then the gravity of those things was able to slow down the expansion. But once the expansion got big enough, the density of everything else was going down, and then the gravity was no longer strong enough to slow down the expansion. And then the dark energy took over and made the expansion go faster. And that, so far, everything we've seen is consistent with that picture. But there's a measurement we're trying to make. We're making a measurement of what's called the equation of state parameter of dark energy, which is measuring. It's a measurement. It has to do with the pressure and the density of whatever this stuff is. And that number, if that number is exactly -1, then we have a cosmological constant, and we know exactly what the evolution of the cosmos is going to be. If that number is anything at all less than -1, then that's the kind of dark energy that leads to a big rip. And so the problem is, if we're trying to measure that number and we are just continually zeroing in on -1, we're never going to have it so precise that we can completely rule out any other number, right? Like that we completely rule out something that's not exactly -1, right? There's always going to be some error bar around there. But we can measure that number, and we can measure if that number changes over time. And so far, it seems like that number has not been changing over time, and it does look a lot like -1. But we're getting more data. There are a couple of cool new observations that are going to be happening. There's the James Webb Space Telescope that's going to look at some very distant galaxies, and there's the Vera Rubin Observatory that'll carry out the LSST survey. I don't remember what there's a survey that the instrument used to be called LSST. Now the survey is called LSST, and the instrument is called the Vera Rubin Observatory. But what it's going to do is it's going to measure millions of galaxies across the universe and map out the universe with extreme precision, and that will give us way more information about dark energy and how the universe has been evolving and will continue to evolve, presumably. So there's those things, and then there's also, theoretical work around things like maybe if you modify gravity, it'll change some of these pictures, and so we can do tests of gravity and tests of general relativity, Einstein's theory of gravity, and see if tweaks to that will give you a different answer for how dark energy is working, and maybe dark energy can be something different that changes over time in some interesting way. So there are lots of measurements around that, and then there's just advances in theory, and maybe we'll find some cool new ideas for dark energy in the theory space, because there's still some major theoretical problems with the cosmological constant. It's an idea that's been around since Einstein, but it doesn't play well with quantum mechanics in complicated ways, and so maybe we'll find some better solution for that as well.
I meant to say at the beginning, and so I'll say this now, that I imagine that some of the people watching may have questions for Katie. And so the way we're handling questions for you people out there is that you type it into the chat on the YouTube channel. And we have, as you know, folks who are monitoring the chat, and they can bring your question into the room. Oh, looks like we have one.
Well, just a point of clarification that's requested from the chat. So when we were looking at that graph of metastability, that point, what exactly is that point? Is that us where we are? Is that the universe as a whole? Some people in the chat were wondering if you could clarify that a bit.
Yeah, so what that is that point is, it represents the value of the Higgs boson mass and the top quark mass, and those are parameters that fit into our mathematical model of how particle physics works in our universe. And so it's really a question of, I mean, it's often, we talk about it as the stability of the universe, but it's really the stability of how particle physics works in our universe. So if we were at a different point in that graph, then you would have different relationships between the particles and the fields and so on. And those would be more or less stable in the sense that, so the thing that's unstable is that if you kind of increase the energy in the Higgs field, you can kind of change its value in a certain way, and it's complicated to go through this. So the laws of physics are okay. Well, the laws of physics are energy dependent. Which is why if you smash particles together at higher and higher energies, higher and higher speeds, you get different answers and in interesting ways. That's why we need huge particle detectors or particle colliders to crank up the energy to see what the laws of physics look like at higher energies. And basically, this instability thing is a statement that at high enough energies, the laws of physics break in such a way that you really don't want them to. And it's not because you can actually reach those energies in space. Like, particle collisions in space or something can actually reach the energies that would give you a different answer in terms of like change the laws of physics in this unfortunate way. But quantum tunneling events can kind of randomly take you to these parts of these different parts of the sort of abstract mathematical model space of the physics, and change the laws of physics locally in a way that would propagate out in a bubble. So unfortunately, it is a little bit technical. I do my best with analogies in the book I think you
did a good job. That explained it to me. We do, and then we have another question. This one's a bit more of a fun one, but Janelle asks, which of these universe ends, if you had to see one in a science fiction story, which one would you like to see happen in a science fiction story the most?
In a science fiction story, so I think that the problem with the Big Crunch is I think that would just be a horror story. I don't think that would be science fiction. I think that would just be I find that one the most terrifying and like horrible, because you would see like the universe, you'd be being cooked, you'd see it coming, and it would be very upsetting. So I don't like that one. The vacuum decay is too quick. You don't like, I've thought about trying to write that into a story myself, because I thought it'd be fun, and it's just like you don't even notice it, right? Like it happens at the speed of light. You don't notice it happened. There's no dramatic tension, like nothing. It's just
be a very short story. One day you're there.
Yeah. You wouldn't even know it got you. So that's no good. And the heat death has been done in various pieces of literature, but it's a little bit sad. So I think you have to go with either the Big Rip or the bouncing cosmologies, which I also talk about in the book. The Big Rip would be interesting because you would get to see the Milky Way like sort of drifting away. And you would get to see the outer planets spiraling out into the void, and then it's only like something like an hour before the whole universe is destroyed that like the Earth blows up. So it gets more and more dramatic as you get closer to the end, and that would be kind of interesting in a science fiction story. And then the bouncing cosmologies could also be quite interesting, because there are kind of possibilities of like sending information through. And I actually have read a science fiction story about one of the bouncing cosmology scenarios, and I talk about that in the book. Actually, I have a shout out to that story because it is kind of cool. So,
well, this is a good moment since you mentioned the book. And David, I was going to come to you in a sec, but no, stick around, Brennan, because there are more, I'm sure. And so because we want Katie to sell some books, I wanted to have people buying her book and reading it. So here's the book again, and you can get it on your lovely, no brick and mortar store online. But even better, if you live here in Los Angeles, you can go to Skylight Books, because I believe, Katie, you sent some nameplates, some
yeah. So I have these little signature cards, book plates, and I sent a pile of them to Skylight Books, and so you can get. So I didn't physically sign the book. Signing books during a pandemic is difficult, but you can get a sticker that I signed stuck into the book, and it's close as you're going to get to a signed book at the moment.
Perfect COVID solution to a book sign. Send the nameplates. And so she's not in person at Skylight Books, but also for those of you who know, here in Los Angeles, Skylight Books is right in our own local Los Feliz neighborhood, just below Griffith Observatory. You literally can look up from Skylight Books and see us. So we encourage you to, do the in-person thing, get one that's signed. And
you can probably do a curbside pickup or something like that, and do it in a very responsible way.
Phyllis is doing very well, and so come and enjoy a nice leisurely stroll past the bookstore. So David, I know you said earlier you had some questions. Did you want to ask?
Well, one of the questions came from Twitter earlier, and you answered the particle death one wouldn't hurt because we wouldn't see it coming, we'd just die. But would the Big Rip hurt? Would that one hurt? Because you said there would only be an hour between.
Yeah, I think, unfortunately, I think it would. So the problem with the Big Rip one, here's what you do if you want to survive as long as possible during the Big Rip. You don't want to be on the Earth, because the Earth is going to be ripped apart. Like basically the larger the thing is, the earlier it's broken apart by the force of the dark energy. So you want to get into the smallest space possible. You don't want to be dependent on the Earth. So you want to get a little tiny spacecraft, or maybe just like a space suit, and be out there away from things, have a very small amount of space, within your little region, because it's the dark energy in the space that's going to get you, right? And you can watch the Earth get ripped apart, and then very shortly after that you die. And because it's I think it might hurt. I don't know. I don't know what happens to you if it's dark energy that's doing this. Maybe it's I don't know. Maybe you don't feel it quite the same way because it's just the space is actually getting bigger. And I don't know. But
what you're saying is have one more glass of wine as you watch the Earth get ripped apart, so you fall asleep and you don't feel a thing.
Sure. Yeah.
It's a little tough through your visor on your space suit.
Yeah.
And did you have other questions, David? Just because I have.
Well, most of them were answered. I was curious about which of these you would prefer to see. The science fiction question kind of answered that one. Do you have a feeling of which of these is actually true? Just sort of a gut feeling on it. I know as scientists we don't go on that at all, but which do you personally think is going to happen?
Well, so I mean, the heat death is the one that's, I think, taken most seriously within cosmology, because it's sort of the simplest model in a lot of ways. You don't need to introduce some new thing. It's just, it's cosmological constant, and it's the evolution that we see happening now. But if you talk to particle physicists, they talk a lot more about vacuum decay, while at the same time acknowledging that we don't know for sure it could happen, because maybe sorry, I'm distracted by your cat. Yeah, so we acknowledge that we don't know for sure if vacuum decay could happen, because maybe things change at different energies. But if vacuum decay were possible, it would happen before the heat death was complete. So that would be the one that would happen first. But I think the heat death seems to be more likely.
Yeah, with vacuum decay, is that the sort of thing that a mad scientist could create in a lab and kill us all?
No. I mean, so there have been a few papers written about how hard that would be, actually. So, it's not clear that there is a physical way to do it on purpose. That's still slightly an open question. Certainly not with any kind of technology humans have any sort of access to, but maybe not with any technology even conceivably possible.
I want to ask a question, Brendan. Are there any from the web? Because I have one, and then if you want to come back, or just keep watching, and I have a question for you, Katie.
Yeah, I'm coming through. I'm gonna hop out of the video part of it while I keep looking for stuff with the other moderators.
So we won't keep you all night, because let's remind everyone that Katie's on the East Coast, so it's getting past 12:30 at night for her. But I was struck very much, and in fact, I was thinking about this when I was looking at the book. And you said part of the reason you wrote it was that things have changed so much recently, and one of the things that struck me in the book was that you said not everybody agrees on what the end will be, but everybody agrees there will be an end. Where when I first went to grad school, steady state was still something people talked about. It was largely gone, but that was still considered a viable debate within within astronomical research circles. And I was in grad school before the Kobe result came out. So, there were still people wanting to say that the cosmic microwave background radiation was not the thermal remnant from the Big Bang. So, I guess I'm more than anything, I'm saying my age, but my point is, it's a big shift. I mean, the resistance to moving away from steady state into a Big Bang cosmology, was so deeply ingrained from cultural ties, religious beliefs. People did not want to give up the steady state, and now steady state isn't in the picture. So I'm curious about, sort of what you think that means for society. What are the spiritual isn't quite the right word, but it's more like psychological, psycho-spiritual level of the difference between a universe that goes on forever and a universe that definitely ends.
Well, it's interesting. Since writing this book and since talking a lot about these ideas, I've heard a lot from religious people from a number of different traditions, and a lot of times the message they have for me is, my religious tradition predicts exactly what you're talking about. So although although the steady state idea, the idea that the universe is just gonna, has been here forever and is going to stay the same forever, is appealing in a certain to certain kinds of religious thinking. It's also maybe appealing the idea that there was, somebody started everything off, and so I know that a lot of people will say, oh, I don't think the Big Bang is inconsistent with my theology, because maybe God that did that, and that's definitely something that a lot of people are comfortable with. So I don't know. I mean, I still do also encounter resistance, not among astronomers or physicists, but among members of the public who say that it's silly to say that the universe could end. And a lot of times they, they bring up like, oh, well, you can't create or destroy energy, and therefore the universe has been around forever and will be around forever. And these kinds of ideas that are, not necessarily true in the way that they think they're true, but ideas that are sort of comforting, that you can't, nothing can be created or destroyed, it's just changing form. And I think that's an idea that's quite appealing to a lot of people, like it's just changing form. And people even talk about that as a way of talking about an afterlife too. So and I think that's not how we in physics talk about these things. It is true that energy changes form in a lot of situations, but on a cosmic scale, saying that nothing can be created or destroyed is not, it's not a principle that we hold dear, or that we think is necessarily valid. So, but culturally, I see why that's appealing. So I think it's there's kind of a mixed response to the idea that the universe is vulnerable to destruction, and that it has been evolving over time. But the idea that it's changing is certainly more accepted now, and I do think that's interesting that we're like, okay, I guess the universe does change, it has evolved, and but maybe there's still a way around it, and within physics there doesn't seem to be, but culturally it's just a mixed bag.
Yeah. Well,
I do have one more quick question. This one's actually from one of our moderators. They're asking, you were talking about, you've interviewed people and asked them what they feel about when you talk about the end of the universe. How do you feel about the end of the universe? In brief, of course, not
Sure. Yeah. So when I was writing the book, and I was writing about how everybody else is responding to this question, my one of the pieces of feedback from my editor was like, oh, you should really put in a lot more of your own response. And I was like, I just don't know. I'm struggling with this. I don't know what I think. And I don't, in the book, I have a little bit of, maybe I come to a little bit of a conclusion, but I'm still not entirely sure how I feel about it. I think I'm more at peace with the idea than I was when I started writing the book. But I still do find it kind of difficult to grapple with the idea that the universe doesn't go on forever, and that maybe, if you look into the far enough future, humanity doesn't really have a legacy. And I don't know, like that's still upsetting to me. And I'm still not sure how to conceptualize that. So I'm going to just hedge a little bit right now, but
of course, no, it sounds like we have to read your book to get a little bit more of a taste.
I think so, yeah.
I don't know. Personally, 2020 is making me grapple with the end of everything. So I think your book is a great title to read to kind of cope with it all. So that's my take.
I do think that it's thinking about the far future of the cosmos, and thinking about kind of how we fit into this much bigger picture, can be a helpful thing when daily life is overwhelming. I do think that if you're sort of feeling like trapped in your own little space, watching the world fall apart around you, thinking about this much bigger picture, and the evolution of the cosmos, and these giant forces, and how everything fits together on this much bigger scale, can be kind of a nice escape and kind of comforting. And at least for me, I find it helps me put things into perspective in a way that I appreciate.
Well, that is a nice segue to saying it's the same thing as looking at the night sky, I think. Whether you're reading about it and conceptualizing, or just going out and looking at that beautiful Jupiter and Saturn and Mars that I hope you will all go out and look at. It's a wonderful calming experience to see the larger context, for sure. It's late. I want to just finish by saying thank you for all of the work that you do in science communication. There has never been a more important time for, well, maybe every generation says that, but it sure seems like a pretty important time to be thinking about science and understanding what science is and how it works and how it affects society. And so I don't know if you have any comments you want to say. And the comment I want to make is to say thank you for being such an effective communicator and for keeping people engaged with science, because it is such an important time for people to understand it.
Thank you so much, and thank you to all of you at the Griffith Observatory, and the work that the observatory was hugely influential for me, and I know that it's such an amazing resource to have in the LA area, and these kinds of programs, reminding people to look at the night sky and giving some people some connection to what's going on in space. I think that's hugely valuable. So I really appreciate the work you're doing as well.
Well, thank you so much, Katie. And just to finish, I can see that Matthew has put up our final slide. So we want to encourage you, first of all, to follow us. But we had kind of a crazy and different idea for this month's show to end it. And that is that I know there are several of you I can see on the chat, names I recognize because you follow us on Twitter. I run the Twitter one. I don't know how to do Facebook and Instagram, but I do read Twitter, our Twitter feed. And so we thought it might be kind of fun to meet some of our followers. And so we're going to end the evening with a little bit of a I guess I'll call it a game or an invitation, that if you follow us on one of our social media accounts, if you put in the chat that you would like to join us in the Zoom room after we shut this down, we're not going to broadcast what happens in the Zoom room, but we would love to meet you. And so if you just put in the chat that you'd like to join us in the Zoom room and tell us what your handle is on whichever social media platform you're using, then we will DM you, direct message you with the link to come into this room. And so I don't know, we may get nobody, maybe it's pretty late for everyone, but I think we usually stay after the show a little bit and talk amongst ourselves. So we thought, well, maybe if there's some followers who want to join us for that while we kind of debrief and relax a little after the excitement of our show, we'd love to meet you. So with that, let me just do this one more time because this is important. And thank Katie very, very much for coming. And
thank you.
We appreciate it. And until the next time, thank you. And to all of you, thank you for coming and joining us. And perhaps we'll see you in the Zoom room. And have a great August. Stay safe, wear a mask, be careful. And we will see you on the first Friday of September. So that's it, Matthew. You can cut the feed.
Thank you, Katie. That was really, really nice. That was a great presentation.